Okay, hello, thank you to the video. Today I'm going to show you how to derive the arithmetic series formula from the 1 to 100 addition problem that Carl Friedrich Gauss had to do when he was supposedly an elementary grade schooler. So the 1 to 100 problem, or the problem of adding all the numbers between 1 and 100, seems to be like an insurmountable task, right? Because you have 100 digits from 1 to 100. This ... means stuff in between that I omit. For example, like a 99 and all other numbers. And if you were to go and add them up, it would take a really long time. I mean, 1 plus 2 equals 3. And then 3 plus 3 equals 6. 3 plus 4 equals 7. That would take forever. That would take forever, right? But actually, Carl Friedrich Gauss said, no, there's a trick. There's a trick we can use to exploit to find the sum very quickly, just using a little trick in algebra. And this is how he did it. First, he called the sum of all the counting numbers from 1 to 100 S. Let S equal 1 plus 2 plus ... plus 99 plus 100, and we have everything there. He said, let's create a copy of this equation. Create a copy. I might even call this a copy principle. But because the order you add doesn't matter, he said, let's go and take this entire list and flip it from right to left. So the 100 goes here, and as you will see here. So basically Gauss reversed the direction. And then in this case, he noticed that if you add all these summons vertically, you will always get a constant 101. So S plus S, you get 2S, so you get 2 copies of the sum. You get 101 plus 101 plus ... plus 101 plus 101. How many copies of these 101s are there? There are 100 of them, because we looked at a list of integers from 1 to 100. So this is the same as 2s equals 100 times 101. Now to solve for s, we divide both sides by 2. So we get s is this, 100 divided by 2. And now we're really not going to care about the answer of this result, although you can compute it if you want. But I'm going to express this 101 in a slightly trickier way. 100 plus 1. And the reason I did this is I would like to emphasize these two terms, because this 1 here is the first term in this list of summons. 100 is the last term in this list of summons as well. This S, which is adding the numbers from 1 to 100, cannot just be generalized for 100. You could do it from 1 up to any consecutive integer n with a common difference of 1. That's what it means to be a consecutive integer when we're talking about the theory of arithmetic sequences. And I remind you that an arithmetic sequence is described by this: un equals u1 plus n minus 1 times d, where u1 is the first term, un is the nth term, d is the common difference, and n is the counting number. Remember, it's got to be a counting number, so we're dealing with sequences here. It's the number of terms, or term number. So then this same result generalizes for s equals 1 plus dot 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 plus n. And since 1 is the first term of that arithmetic sequence and 100 is the last term of that arithmetic sequence, I can rewrite this as s equals n times n plus 1 divided by 2. Do you see? It's almost the same as this 100 here, except I replaced it with n. And this has a particular nice geometric application. This is called the triangular numbers formula. Which counts the amount of dots that are in a triangular array, but more on that later. But the thing is, we can generalize this even further, because this is a sequence with a common difference of 1. This is for b equals 1. And we start with a use of 1 equals 1, and a use of n equals n. But who says we can't do this for a more general u1, d, and un in general? So this term now, instead of 1 in 100 and 1 in n, the first term will be replaced. So generalize. The first term here will be replaced with u1. The last term with un. Sorry, that looks very messy. And then you still have this n over 2. And I did this here because if you were to do this kind of argument in terms of this general expression here, you have to create a general copy of this expression, it's going to look really, really, really messy. But yeah, this, you just quickly swap the terms. Swap 1 with 1 to u1, and 100 to n to un. And that's, ladies and gentlemen, the arithmetic series formula. Yeah, sorry, let me rewrite. That looks atrocious. There. So I hope that explains to you how we get this very nice result from this trick that Gauss did. And I'll mention this because I don't think I emphasized this enough. You could reverse the string of the digits being added because addition, the order doesn't matter. In a fancy word, we say addition is commutative. And from that, we managed to get this magic over here. So yeah, I hope you enjoyed this video. We'll go and explore more things such as the how to derive the finite geometric series formula, and then the infinite geometric series. I hope to see you in the next one. Bye-bye.